Okay. Hello, everyone. Welcome back to our monthly seminar, Women in Solar Physics, where we are celebrating women who do research in solar physics in honor of the solar maximum that's happened this year. And so with us today, we have Dr. Sneha Pandit, who is an amazing woman doing research in the sun, and she's currently um, a postdoctoral fellow at IUCAA in India, and she did her research in solar physics using ALMA, and she has so much experience with the sun, and she has so much interest in various aspects of the sun. And she even researched the sun using simple molecules like calcium. So we have a lot to learn from her today, and I will invite our guest. Thank you so much for joining us. And my name is Naomi Asabre Frimpong. I'm the Deputy Director of IAU Office for Astronomy Outreach, and we are happy to have this wonderful lady join us and talk about her research. So I'll hand it over to you, and please tell us about all the wonderful things you have for us about our life under the sun.
Thank you so much. Thank you so much for having me. And yes, I did my PhD using ALMA data, and currently I'm using Parker Solar Probe data to understand the sun and its atmospheres. Um, but the topic today for this talk is life under the sun and exploring habitability using our sun. So this is kind of the motivation with which I started my journey of for like learning the about the sun. It is in a way related to what I do, and it will show us how solar physics research like studying the sun is going to help us in various everyday manners and even in long term as for the humanity per se. So let's dive in. Um, so by the end of the talk, we should be able to answer these three questions. What is habitability? What are the requirements for life? And why does Earth around the sun has life? Okay, so there are two parts. In part one, we will understand about habitability, and then in the second part, we will see how directly we can study uh, the symptoms for habitability using the sun. Okay, so this is our roadmap for the part one. Um, Firstly, we will start on a philosophical note about are we alone in the universe? Are we accompanied by some aliens and such? Because that's how the study of astronomy in a way started. Uh, and there is this very famous quote by Arthur C. Clarke. He was a science popularizer and science communicator. So he says that two possibilities exist. Either we are alone in the universe or we are not alone in the universe. If we are alone, then it's such a huge vast universe, and with current advancement of technology, we are seeing farther and farther out, farther away, and the universe is expanding and it is becoming bigger and so on, and we are alone. That is terrifying. On the other hand, if we are not alone, if there are other life forms, and one, we cannot contact them, maybe we are not intelligent enough. Two, they don't want to contact us, they don't deem us intelligent enough, or they deem us very scary. So this is all equally terrifying, and that's why we need to know more about this. And this is the motivation in general for people to study about stars, about stellar clusters, about different galaxies, and this is one of the major motivations philosophically speaking. Okay, so in the roadmap, we are going to define a few things in order to understand habitability. So if we are not alone in the universe, then there are some other planets, which we call exoplanets, where there must be some kind of life forms. So what are exoplanets? As per NASA, standard definition of exoplanets is any planet which is beyond our solar system. So For example, in our solar system, we are 8 planets. There are some smaller planets, there are some asteroids, and this whole system is in a way gravitationally, magnetically, and energetically governed by the sun. So this kind of systems around other stars can exist. It exists in multiplicity. So there are many planets which are orbit around stars, but there are a few planets which are rogue, which do not orbit around stars, and those are not of interest for us in this talk right now, because we know a star planet system, which is Sun Earth system, which has life. So we would like to, in exploration for habitability in around other stars, we would like to find a similar system where there is a planet roaming around a star. So now we know what an exoplanet is. Um, but why does it matter that the star and planet should be tethered to each other in a way? Because the star-planet interaction kind of sustains us. So one quick detour, because this will be very important for us in this talk to understand how we understand about stars or about sun. So we have observatories. We have observatories on Earth. We have some observatories in space. This is one of the observatories which is launched by India in 2 years back now. It's called Aditya L1. Aditya is the name, L1 is the place where it is. So L1 is a Lagrange one point between Sun and Earth, where this observatory continuously observes the Sun. And this was made from the instrument suite, which observes the sun in UV, ultraviolet wavelengths, was made from a team by the institute where I work. So it's a very proud moment. So what they did was they made the instrument, they fit it inside the rocket, and they sent the rocket out. And then since then we have been receiving this kind of amazing data from the instrument. And if you see, like in throughout the talk, you'll be seeing several images of the sun with different colors. First, the colors are not real. What we get is intensity maps. So at particular, for example, if we take this map of the sun, so this is called full disk data. We have like the whole disk of the sun. Then there are these dark spots, there are these like bright ones, then these are neither bright, neither dark, and so on. So we only know the intensity. So we only know the numbers where, so this is very low number, this is very high number, and that's it. But we observe these at different wavelengths. So in different wavelengths are formed at different layers in the atmosphere. So we can actually see how at different heights from the so-called surface of the sun, we'll get to that in a few slides. So at different heights, how the structures are, how the sun is behaving, it might be different. So if you notice here, these bright features that we see here are not that visible, but these dark features are way more visible. So these are basically different features that are present on the different layers of the sun that we can that are more pronounced in different wavelengths. And then for us scientists to be, happy or interested in our work and, get this mind map, we put different colors for different wavelengths so that we quickly know, oh, okay, so this layer is going to show us the sunspots. And we quickly know, okay, so this brown color, so that means this layer is going to show us the plage regions in the chromosphere. So these are the words we will get to, but these are called false color images. So any image of the sun is just intensity map, nothing else. No colors are seen. Okay. Anyway, this is in UV, so we cannot see UV colors by eyes. Okay. So these images were from Soot. Now, NASA has sent an observatory way long back in time in 2010. And that observatory has been observing sun in other set of wavelengths. And you can see like there are these different features. So this is combination of three different images. And there are this is a coronal hole, and there are several continuous movement of the plasma. There are these eruptions, and continuously something or something else is happening on the sun, and something is coming out of the sun at the same time, and that affects all the planets around the sun, but Earth has life on it, so that affects Earth the most. um How this is a artistic or cartoon image, what we call it. It's an artistic representation. So if something like a energetic event is happening, a flare is happening, or a coronal mass ejection is happening, that is going to spew a lot of plasma. So plasma is what the stars are made of, and it is but charged, magnetically charged, electrically charged, heated gas. So all the mostly the electrons and the core of the nuclei of the atom are separated. So it's very highly charged, and then it is very light as well. So it is thrown out of the sun, and then that moving charges and magnetically active plasma is going to hit the earth. But the earth has a good magnetic field around it, and this plasma is kind of drained because of the magnetic field. It doesn't go directly to the earth. It follows these magnetic field lines, and most of the times the earth is saved from this energetic heated particles hitting us. At the same time, this phenomena creates auroral dance in the skies. So the northern lights or the southern lights that we see are because these particles get drained in the magnetic field, and the polar regions, the magnetic poles, these particles kind of accumulate and then interact with the atmosphere, where they create these visible green or sometimes pink lights. um, and yeah, uh, but except for the auroral dance, most of the impact of this charged and electric plasma is harmful for the life on planet. So this is one of the examples of flare. So this is again from the same observatory, the NASA SDO observatory. Um, and this kind of event can cause these huge plasma eruptions. Another event, so you can see like here there is something happening, some small I can play it again actually. Yeah. So some small loops are moving within them, and suddenly there is a prominence. So there is this plasma thrown out, and it gets heated a lot, and that heated plasma was sent out in the solar wind, and then it will hit the planet. So having a good magnetically, I would say, compatible star planet interaction is very important for habitability. The next important thing is having atmosphere around the earth. We will, for one slide, we will go into a bit of biology because it is important. We are talking about life. So we know that most of the cells that any animal, plant, and all other kind of life forms are made of are 70% water. So we need hydrogen and oxygen for that. And the 30% biomolecules, they are formed of carbon, nitrogen, and phosphorus basically. So having these molecular traces in the information that we get about the planet is very important, because I mean there can be other kind of life form which is not carbon based, but some other element like silicon based and so on. People, the astrobiologists as we call them, they explore these possibilities. But since we already have a data point, only one data point where the um, life is such with carbon molecules and RNAs and DNAs, we would like to start our search from that platform, let's say. Yeah. So most of the biomolecules are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's it. So we would like to see that. And there are these extremophiles which are studied in order to understand that, which are in hydrothermal vents or highly saline salt waters, even in the sand of the oceans, and highly cold environments in Arctic marine sediments, and so on, which can survive several extreme conditions. They are sent to check on spaceships and rockets to see if they can survive the space environments, and if there could be these kind of small, like microbiome animals away in other exoplanetary environment. This is again an artistic representation of Venus. So Venus has highly sulfuric environment, and there are traces that there used to be water, but then water and sulfur, when they react with each other, they form sulfuric acid, which is very dangerous, which is highly acidic and very toxic as for the life as we know it. And that's why on Venus it is very difficult to imagine having life, even when the sulfur content was lower. And yeah, and another extent, we have Jupiter in our solar system, which is gaseous. So this is again another artistic representation of Jupiter. Jupiter is a gaseous planet, right? It doesn't have a rocky surface like the Venus or Mars or Earth. um, so there is firstly no surface for life to stand. But then there are these satellites of Venus, which are, for example, Europa or Titan. They have surface, they are rocky, and there are traces of water on them that the planetologists study. And it is possible that with advancement of technology, this is science fiction, not science, we could go there when Earth is unlivable. But yes, we should keep the Earth livable, not this is not good. Anyway, so the having atmosphere around Earth is which is keeping the Earth warm enough, which is keeping the sunlight inside the atmospheric layers to keep the temperatures not too warm, not too cold. That is one of the major criteria for having life on Earth, because outside the atmosphere the temperatures are very low. Below the surface of the Earth, near the core, the temperatures are very high. Near the sun, the temperatures are extremely high. So the life as we know it cannot survive these drastic conditions. So to have flourishing life, the atmosphere plays a very crucial role, that it keeps the temperatures near the surface of the Earth and surface of the water on Earth, so that water is in liquid form, so that it nourishes all the plants which can do photosynthesis in the temperatures that are uh, warm enough, nice enough. The last part is having the star to be well behaved, as we will like to call it. So this is one of the images of all the currently live satellites. So there is a lot of space debris of satellites which are dead now, but these are all the live satellites. And I'll just like to take a moment so that you can imagine how many these are. So the space debris is a lot, but the current live satellites are in the ballpark of 15 to 20,000, and they help us in all the navigation, internet. Our like we are basically, as the urban society, we are completely dependent on satellites, because we cannot live without internet. We cannot live without GPS. And these satellites are going to be affected by the plasma eruptions that I showed before, that come away from the sun. And then these satellites being out of the atmosphere, the dissipation of magnetic field that we showed before, it might not be enough, because these are farther away from the surface of the Earth. So that is one of the reasons we need to understand how the host star behaves. Another thing is, if this mass ejections or plasma eruptions are very strong, and they penetrate the shield of the atmosphere, they can interact with the live wires, the electricity wires that we are entirely dependent on now. And this has happened a couple of times. This usually happens in the polar regions. So in the South Pole, there is hardly any life. But on the north, near the North Pole, near the Arctic ring, in 1978, there was a major incident in Canada, Another incident was in 1972, I think, in Sweden and Norway, because it is on the Arctic ring, and we saw that the magnetic field lines kind of converge there. The charged particles of plasma, they kind of entered inside the electric ring and electric wires, live wires, and they just fried the whole system. So yeah, so there is always this fear or uncertainty with very strong solar uh, ejecta coming out. But yes, we can also see northern lights. This small person is me looking at the northern lights during my PhD when I was in Norway. And this is probably the only perk of having active space weather phenomena. So with all the information that we have now, we can finally define what is habitability and what is required for habitability. So there is this habitable zone that we can define, which is for given size of planet, for given size of star, and the activity of the star, where the planet should be. And currently the earth is right in the habitable zone and it is all good. But if after a few billion years, mind you, billion, it is a huge number, it's not going to happen ever in our imaginable lifetimes, but after a few 5 or 6 to 8 billion years later from now, the sun is going to turn into a red giant, which means it is the atmospheres around the sun are going to be expanded, it will become huge. And because of that, it will basically engulf the first two rocky planets. Earth will be very close to the corona of the old sun, and it will no longer be in habitable zone, and it will be Jupiter and Saturn will come in habitable zone. And now the discussion about the satellites of Jupiter and Saturn, which are rocky and which can have water and which can have some carbon or oxygen, that comes into discussion, because probably 8 billion years later, there is nothing left on Earth. But probably if our 10 to the power 9 times grandchildren are there, they would like to move to habitable zone before this happens. So this is kind of the one of the reasons people would like to discuss about habitability. How do we know about other planets? And this is like transit light curve. That means there was star, we know how the light of the star looks like. And if there was eclipse of the planet around it, we can see that the starlight is blocked, and how much and for how much long time the starlight is blocked. Based on that, scientists can make predictions about the existence of planet, its size, its shape, its mass, and so on. Okay, so what is habitability? We started with these questions. What is habitability? What are the requirements for life? And why does the Earth around Sun has life? Or how do we find other habitable planets? That's the same question. And we need adequate environment for life, or equivalently for liquid water we need a solid surface. As of now, we need oxygen rich, non-burning, non-acidic atmosphere. Planet and host star should have complementary magnetic field strengths, so that the if even if the host star is too dramatic, like it's spewing a lot of flares and a lot of ejections, it should be drained within the magnetic field. At the same time, the host star should not be too dramatic. So that will help us. And the energy should come from the host star or stars. And any star planet system where all the above criteria are satisfied um, is is one of the candidates for habitable place. And then we can start talking about the life on that place. Okay, so the first part is done. Now we will understand the the star planet system that we are on. So how, why, and how can we understand this system better? and use this as template for searching for other systems. And for that we need to understand stellar activity, because the star is not the same all the time, and we will get to that. So first we will understand what how the sun is. um, So there is core where the nuclear reactions happen, they produce energy. That energy is first radiated away in the radiative zone, and it takes a lot of time because it's very dense. There are a lot of particles around this inside and around this core. So, for example, if you are in a very, very busy city and you want to go from a train station, from a platform to outside of the platform, so I usually give an example of Mumbai or New York or Tokyo or something like very dense. And then there are so many people, you know that you want to go out, you want to, let's say, go to the ticket office and then out to catch a metro or whatever. But there are so many people coming, you cannot go in the straight line. You go in uh, zigzag manner, and that is what happens in the radiative zone to the photons. They want to expand, they want to go out, but there are so many particles and so many other photons there that they just collide with each other and they take these zigzag paths. So after the radiative zone, there is this intermediate region that we call tachocline. But after that, there are these convective zones. So one of the easiest example for convection is having a pot of water and then you put it on heat. And if you put either easy thing is putting tea leaves, because then you can see the colors moving. Then the top part is cold because heat is coming from down. So in this case, the radiative zone is heating the convective zone. So the heat is coming from down, and this chunk of plasma which is near the radiative zone is moving up. It's heated, it expands, it gives the heat away to nearby particles, nearby plasma, and then it cools down. It becomes a bit dense, it becomes a bit cold, and then it falls down. And this keeps on going, and that is the convection cycle. And because there are several convection cycles here, the region from where the photons can escape in more or less straight lines and reach us, that region is called photosphere. So basically, the sphere from where the photons come out. And that photosphere is it has this convective zone pattern, but when we look it from outside, it looks like we call it granules. So it's called granulation pattern. Okay, so then there is photosphere, which we can see, and out of there is so the density keeps on decreasing. By the way, we'll see it in the next slide, and the temperature should decrease. So from the core, which is multi-million, it is around 10 to 15 million Kelvin. The temperature keeps on decreasing and becomes around 6,000 Kelvin near photosphere. From photosphere, it should decrease. So we are coming away from a hot object, so the temperature should decrease. And it does up to some extent where it goes to nearly 4,000 Kelvin and it starts to pick up again. The temperature increases. And when we are even further out, for the region which we call corona, which looks like the crown of the sun, then the temperature is even higher and it becomes 1 to 2 million Kelvin again. And that is one of the research topics. So this happens in many main sequence stars, most of the main sequence stars. So there is something called main sequence stars, which are very similar to sun. Then there are other kind of stars which are quite dissimilar to sun. So stars which are similar to sun, we see this temperature decrease till the photosphere or the slightly higher region from the photosphere and sudden increase. And we need to understand that in order to understand the interaction of that host star with the planets. Um, Another thing that sun does is called differential rotation. So for Earth, the whole sphere is a solid on the outside mostly. So it rotates as a whole rigid object, but sun is made of a charged gas. So it does rotate, but it rotates at different speeds at different latitudes. And because of that, the magnetic field of the sun, not only because of that, but because of also because of other events inside the sun, inside the core of the sun, the magnetic field of the sun is quite complicated. So for the earth, we have this dipole and then north and south pole, and that's it. But since the plasma, which is charged and magnetic, and it is moving, and when charged particles move, they create magnetism as well. So the magnetic field of the sun is quite complicated, and as we see, the plasma can go out and so on. So the um, how to kind of understand these magnetic properties of the sun is also one of the challenges that solar physicists like to solve. So this is just an illustration of how strong and how large the magnetic field of the sun can be. So this is just as a representation. This is the whole earth, and sometimes the loops, or in the previous slide as I showed the coronal mass ejections, those can be even larger than the size of earth. And yeah, the sun is huge. We saw these a few in the previous slides. We saw these uh, features on different layers of the sun. So these are sunspots, and these are the granulation pattern that I talked about because of the convection. So this is on the photosphere. Then on the chromosphere, it's called chromosphere because it was first seen in red color, like in the red wavelength, and that's why it's the sphere of color basically. So there are these bright regions which are called plage. So in French, plage means uh, beach waves. So they move. So everything moves. So these are bright regions which are supposed to be more hot than the dark region. And in corona we have like these open field lines, open magnetic field lines, and different structures than the previous two layers. So there can be these standing loops because the coronal plasma is slightly less dense. Then that means that the magnetic field basically governs the plasma. So the plasma moves along the magnetic field lines, and that is firstly very pretty to observe and very difficult to model. Okay, the just check time. Yeah. One of the last topics that we will talk about is the activity cycle. So so this is the previous activity cycle, which in a way concluded in 2020, and the next one started. Um, what happens is this differential rotation and the magnetic field inside the sun, and the let's say the sunspots, they move on the surface because of the rotation. The plages move, the loops evolve, they erupt, and so on. But this is not, so this doesn't happen at the same time all the time. What happens is these features come and go, and they come and go with different frequencies. So when currently we are at the peak of the solar activity cycle, it's usually more or less believed to be 11 years span, where so currently we are at the peak. The sun somehow kind of looks similar to this, where there are several sunspots at the same time, where there are several eruptions happening, flares coming, and so on. Whereas 5 years back or so, the sun was not as dramatic. There were very few or close to no sunspots, very less amount of flares, very less frequent flares. And the reason for this is also one of the topic of debates, topic of research. And we need to understand this solar activity, or even for other stars, stellar activity cycles, because when we are modeling a star and planet system, if we do not know for all the stars in which phase of their activity cycle they are in. And if we are modeling a star planet system and we are observing it in low activity, we do not know how it will be in a very high activity phase, the highest activity phase. And if it is going to be very dramatic, if it is going to be very uh, having a lot of flares, having a lot of ejections and so on, then it might not be possible for that planet to have higher habitability. Whereas if we are looking at a star in its highest activity phase, and we do not know if we are looking at that star at highest activity phase, we are looking at a star and we just know very little information about that star because the stars are far away. So we do not have this kind of this is we call resolved disk information. We just have point. So stars just twinkle on the surface of the sky, right? So we just have points. So from those points, we do not know if this is happening or this is happening. We just have information about the uh, existence of star in a way. So if we understand the solar's activity cycle better, then we can model other stellar activity cycles with the information that we have from them. And then we can talk about the interaction of those stars with their planets in the planetary systems. And that basically kind of helps us to understand about habitability around those stars more. So this solar activity cycle has been studied quite a lot since 1600s actually, and we are in currently solar cycle 25. But you can see like this is the number of sunspots, like percentage of sunspots on the disk of the sun, and that is quite variable. So even if, as of current understanding of the solar activity cycle, even if we understand this as the cycles for the other stars, it is even more difficult because we do not have resolved disk, and we can be in a very highly active activity phase, or we can be in an average or low activity phase for the star. This is one of the favorite diagrams that I have. It's called butterfly diagram, and that kind of shows us how the uh, sunspot area for a given uh, disk, it how the sunspots move on the disk in a way, and it looks like butterfly. It's called butterfly diagram for the sun. Maybe you can look it up uh, and read about it. Okay. One weird thing about the sun is since the observation for the resolved spots on the solar disk started in 1600s, initial period was with a very low activity. So there were these variations in the activity, but when we see variations later in time, these variations were very low, and that's why that's called a minimum. So Maunder was one of the scientists who worked on this. Dalton was another scientist, and they found these minima in the solar activity. And then there is this modern maximum in 1950s. Uh, so this is more or less the 11-year activity cycle. But then there are these minima, and we do not know enough about the variation in the solar activity, why these minima came exactly. And if when we are observing other stars, if that star is in its minimum phase for several hundreds of years, so this lasted for a few decades, right? So if we are observing other stars and they are in their minimum phase or they are in their maximum phase, then prediction about the star planet interactions and habitability are not going to be accurate. So we need to understand solar long term activity changes and cycles better to predict about other stars. I will now quickly go through the other problems that we have. So I talked about, oh, I have a weird thing on screen, but anyway, ignore this. So I talked about the coronal heating problem briefly in the introduction part of the sun, but what happens is the density of the plasma decreases. So this is photosphere, and then away from the photosphere, the density goes lower and lower. And at the photosphere, so this is temperature in the core, it decreases near the surface, and then it starts increasing for in the corona again. That we see here again. So this is called coronal or chromospheric coronal heating problem. So there is heating happening outside in the atmosphere because of the interaction within the plasma. So there are a few theories which are competing against each other, which are they collaborate together to predict if this is enough heating, but there is no consensus yet about the solutions for coronal heating problem. Um, this is a in a way quick detour to what I do currently. Um, so so near the sun, near the chromosphere, the corona, there are coronal mass ejections, and then there is solar wind, which spans very large distances, and uh, it kind of takes these ejections and the masses and in general the plasmas, the particles and magnetic fields farther away from the sun, and that interacts with all the planets. It is like in the heliosphere. So the sphere of influence of the sun is called heliosphere, and this solar wind is all the way till the end of the heliosphere. So to study the properties of solar wind, NASA sent Parker Solar Probe, and it is very close to the sun. It is going as close as 10 times the solar radius of the sun. Um, and it detects the energetic particles, it detects the magnetic field there, and this is one of the phenomena I study, the magnetic fields of the solar wind as of now. So there is one more called Solar Orbiter. It is sent by European Space Agency, and both of these they go farther inside. It's called in-situ instruments, which are going inside the plasma and studying the plasma. And the other set of instruments are remote sensing instruments, which are near the Earth, the satellites, all the images that I showed, like Aditya L1, like the Solar Dynamics Observatory of NASA. These are very near to the Earth or on the surface of the Earth. So these are different kinds of instruments with which we can study different phenomena happening on the sun, around the sun, in the atmosphere of the sun. So there is something called switchbacks, which are, this is like again a cartoon image or cartoon video where the magnetic field kind of switches back, and the probe is going through this kind of structures and studying the properties of this kind of events. Um, I'm going to show you these different observatories. You can pause here and check if you know any of these. How many do you know? You can put in the comments. And now I will show the names of the observatories. So a few of these are from India. So this is Udaipur Solar Observatory. Um, and there is one more in Leh, but I didn't put the picture. Then this Solar Dynamic Observatory and Parker Solar Probe, these are in the sky. These are sent by NASA. This Kodaikanal Solar Observatory is also in India. Then there is DKIST and Solar Telescope Hawaii, which are in the US. There is European Solar Telescope, which is in Canary Islands. And there are many more. These are just a few images that I had in the slide, but there are many more observatories that observe the sun from the ground and from the sky. Now, what happens is if the observatory is on the ground, there is this large layer of atmosphere, and any photon which passes through atmosphere, uh, it gets diffracted, it gets like reflected. It kind of has a lot of noise in it. And when we are looking at these small scale features on the sun, like a small loop or a flare, and these are like small parts on the whole disk of the sun, right? These small noise that we have in the photon can create false information in the image. Now, to get rid of that, we have to process the data quite a lot to make it science ready. Um, uh, so usually the observatories are near water or on top of hills when they are on the surface of the earth, so that if it is near water, then the water kind of cools down the layer of atmosphere on top of the observatory, so that um, there is less noise. And if it is on top of a hill like this one, or so the Hawaii one is near water. Yes, and this Canary Island is on top of a hill. So then you're already getting rid of the dense atmosphere which is near the earth, like near the sea level, but there is still a lot of atmospheric noise. So also the atmosphere gets rid of all the UV light. So we have ozone layer which saves us from UV light or burning for our skin and everything. But we cannot study UV information if we are on the surface of Earth. And that is why we send these observatory in space. So it gets rid of the noise, and it also opens up opportunity to see different wavelengths. But then from space you have to relay the data back to Earth, and in that process there can be inflection of noise. There can be only some amount of data that can be sent, because the observatory is going around the Earth, and the data relay centers are somewhere specific. So um, there is a lot of data observed with different observatories. At the same time, there is not enough data with which we can do science. So this bridging of using the available data to making into like science ready, research ready information, that is also one of the big problems that not only solar physicists but all astrophysicists face. um, this is the last interactive slide. This is one of the latest uh, observatories that was sent, and it made a lot of noise in the media, and it is very promising. So you can pause and think and reply. Um, I will show the answer now. It is James Webb Space Telescope, JWST. I showed one of the ways JWST is going to help us find habitability, because it is going to look at farther away stars with more precision, and farther away planets around the stars with more precision, and then we can have information about the sizes of the planets in comparison to the star. And yeah, we can have more information about habitable planets with JWST, in addition to all other things that JWST is capable of. Okay, so now we will conclude the current problems in solar physics. So one is coronal heating problem. Sorry, I have a typo here. It's coronal heating problem. It's also the variability in the solar and stellar activity, the variability within a given cycle, variability for several cycles, and the large scale minima or maxima that the sun or the stars can have. um, then the solar wind magnetic fields that I work on, and that can lead to having more accurate space weather predictions. I didn't talk about this, the dynamo inside the sun, but it's something somebody else can talk about later. It's how the magnetic field is generated inside the core of the star, and how it is sustained for so long. And then the imaging and noise reduction problem that we have, um, that I just touched upon. And in the exoplanet physics, the detectability and instrumentation limit is something people struggle with. To start with, the stars are not well understood. So the planets around the stars, which do not have their own light, so they only reflect the light that stars provide, is even more convoluted problem. Um, and we will end on a philosophical note, as we started on a philosophical note, that there is something called Fermi paradox. You can look it up. But in one sentence, it is basically, why has no one contacted us yet? Because the universe is so large, so vast, and and as of now, nobody has contacted us. So does that mean we, as life forms on Earth, were a fluke or something that the universe shouldn't have made in a way? So this is basically Fermi paradox. It is something to think about. It's not a research topic for science. It is a philosophical thought experiment. And another philosophical question is, do we want to communicate with aliens? This is very popular with popular science talks. Usually, people like to think about this stuff because it has been all over the movies and literature, and it is something very fun to discuss. But seriously, NASA had, like, from Harvard University, there is a huge radio antenna from which um, there is a continuous signal sent with basic information about uh, human race, history, some philosophy, numbers, and basic language, and so on, for some decades now, and that has not been responded by anybody. So yeah, that's about it. And yeah, Albert Einstein says that the important thing is never stop questioning. So I will leave you with this movie of Aurora that I made during my stay in Norway. And thank you so much. I can take questions now.
Thank you so much, Dr. Pandit, for your wonderful presentation. It was so detailed and there was so much information, and we needed to hear that, and it was amazing. Thank you so much for the wonderful work you're doing and for the presentation. We have a couple of questions. One is that one question, the first one is for me. I want to know, like, there's so much, like, look at the images are showing beautiful auroras happening in the northern hemisphere and the southern hemisphere. Why can't we see it in the equator? Because I'm from Ghana and we are close to the equator, and I also want to see that. Why can't we experience such beautiful things in the equator?
Uh, I reciprocate very directly because I'm from India and we don't see it either in most parts of India at all the times. There was only this one time this year in May, actually, because of very high activity of the sun, we could see it in the northernmost part called Ladakh, which is in the Himalayas. At that time, actually, people from Prague and Paris and like these latitudes could see aurora, but
Mm,
not as beautiful as in the north or extreme south. What happens is there is this um, magnetic field of Earth, and the, let's say there is a coronal mass ejection, and the mass ejecta, it is going to first, it has a lot of velocity and energy that it is ejected with. So it follows that eventually it slows down a bit, and also accelerated by the solar wind at the same time. But when it comes into the influence of the Earth's magnetic field, then since it is a dipolar magnetic field, its poles are near the geographical north and south pole. So this ejecta, since it is plasma, it is charged and it is magnetic, it is going to follow the magnetic field lines it discovers. So then it follows the Earth's magnetic field line, and the near the Arctic and the Antarctic region, there are these auroral ovals. Basically, that means the magnetic field lines are going inside the Earth's core. They are going
mm,
through the Earth. So then the plasma can actually penetrate several atmospheric layers when the magnetic field lines are going to be curved. And
mm,
what happens during the aurora is these charged particles, these are mostly positively charged or negatively charged, depending on how the plasma was. And those particles are going to interact with the atmosphere. So the atmosphere is mostly made of oxygen and nitrogen, and that when those particles interact, these oxygen or nitrogen atoms, they kind of absorb that energy, and eventually they release that energy. And during this absorption and release of energy, the energy is released in optical range. So usually we see green aurora because it is a transition between some oxygen energy levels in the atom. So that energy is released as green light. Sometimes there is some other kind of not the green, but when we see pink or red or magenta colored aurora, there is some other kind of atomic transition that is happening, and that can only happen when the plasma is interacting, when the plasma is in the denser part of the atmosphere. So usually when the ejecta comes from the sun, it comes in any direction, right? But then it gets directed to the polar region of the earth. And if we actually see the northern lights at the equator, it is not good for our any of the communication systems and any of the electrical systems, because it's going to mess up everything. So it is
Mm.
good that it was only in the polar region, where firstly the population density is very less in comparison to the equator, and that's why there are sparse electrical systems and sparse people living. But yeah, I would also really love for the northern lights to be seen near my home place.
Thank you so much for answering the question. So I heard you talk about astrobiology, and I know Perseverance has like a biosignature news coming up. How significant is that kind of news from Perseverance to us now, on Earth, and our interest in the universe and finding habitable zones? How important is this news to us?
So there is already information about Mars having water on its surface.
Mhm.
Um, but it could be that in a few, let's say, million years back, it was viable for life to be present on Mars. It didn't come, or we do not know information about that yet. But progressively Mars has become colder and colder because it is farther away from the sun. And yeah, I- I'm 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 not very aware about exact news that Perseverance is going to tell us, but
Mm.
having this, uh, yeah, I think it is always interesting to have new information, and we can use it. But I'm not sure. I don't know how to answer this question.
But then so that's okay. But going back to the auroras, um, you mentioned how seeing it has such a huge effect on our internet, our GPSs, and navigation. Are there any countermeasures being,
I could not hear your question for the internet and for
done
the.
to help impact on our, systems? Did my
I'm
internet?
so sorry. Probably my internet is not very good.
I
Um,
think it's mine. I was asking whether are there any countermeasures being done for towards the interruption of our navigation systems by, solar flares and auroras?
Actually, we cannot predict the space weather with enough precision yet. So I can quote an incident from 2023 December. Starlink sent several satellites in middle of the December, 16th or 18th, and 1 to 2 days later, those satellites, they kind of lost contact with the Earth, with their respective centers, because of a very large flare that hit, and all the communication parts on the satellites, they just got fried. Um, and we do not want that to repeat, actually. So we would like to understand space weather enough, at least, so that we can close the parts on the satellite which are more sensitive to these kind of plasma or with charged particles, with heated particles, and so on. But we unfortunately uh, we still have long way to go to understand the or predict the space weather.
Yeah, I hope we can do that with the work you're doing and the work of other amazing scientists working on the sun and trying to use it to understand how best we can protect ourselves. I'm sure we'll find a way to put measures in place. Thank you so much, Dr. Pandit, for joining us for our monthly webinars. Thank you for your time. We are really grateful. And thank you to all of those of us, or those of you who join us online, live on YouTube, and those who watch later. We hope you enjoy the talk, and we'll see you again next month for another session of Women in Solar Physics. Thank you for joining us and have a good day.
Thank you so much for hosting. It was really fun to do this talk. Thank you so much.